that data. So, like if you look at how it was split up in the Kaggle comp, so there's 51 experiments.
Yeah, and different, like, because I was thinking originally, like, oh, I could just do one cell type. But it's like, well, that might not give you a good evaluation.
Yeah, but there's, so, just do one cell type. There's the one that's most abundant is called HUVEC.
Yeah, I looked at it.
And it's got like, I can't remember the numbers, but it's got the
Like
most.
21 experiments.
Yeah, that's the number I was making. So I remember. That's good. So yeah, so that's about half. You know, a little less than half. So you know, if that helps, and then just keep taking out something. Yeah. Or sorry, just so if you just reduce that one, that's good. But then if you need to go more, then just start removing experience. And I mean, like the performance will go down. So.
But it'll give you a good idea.
Yeah. Like keep the evaluation set the same, because that's cheap.
Well, yeah, I mean, you can't train the test.
No. Like,
Or
so
you mean
saying,
as far as
don't cut down the test.
Yeah.
Just leave that the same, and then you'll get comparisons to like what everybody else has ever done on it.
Yeah, like you're getting a realistic read that you can like relate to other.
And you'll be worse for sure, but it will be, but it'll give you some sense of how bad it is, and you can, like a standard thing to do. You might not have enough time to do this, but it's like, train with 21, train with 17, train with 13, or something like that. Just kind of see how performance drops off just with some baseline architecture.
Okay.
And then that'll give you some sense of like, like I'll pick 17 because that'll be like that.
So just like under one architecture, see where it really falls off, and then kind of use that as my cut point to evaluate other.
Yeah.
Okay.
Yeah, that's a pretty typical thing to do. Yeah.
I did virtual on Tuesday, but before that I like sitting there. So like the one that's on set. Not very much fit. So you've taken this as far.
So starting with 640.
Yeah.
Yeah. I know the back competition.
Oh, okay. That's good. Just see them in a white or figure out this weekend.
But
Oh yeah.
Okay, I think we just get started. Right on time. How's everybody doing?
Good.
Good? We're dwindling here in the classroom. Everybody has like this, this energy at the beginning of the semester, and then they do one homework assignment, and then it's like, never mind. Well, thank you for coming, all of you who have. It makes me feel wanted, special. Thanks. All right. Well, thanks to Ming Zhen for giving the lecture on Tuesday. I was out of town, so I appreciate that. And any questions from Tuesday's lecture, or any questions at all, just before we get started today? Did you like ResNets? Did you not like them? I mean, they're pretty much the standard baseline now. You see most everything kind of benchmarked, with a ResNet something or other. And then, often if you go and you just like go to Kaggle, for instance, and go look at the architectures that are winning, those competitions. If there are convolutional networks, very often you won't see ResNets, just like plain vanilla ResNets, but you'll see something like a ResNext, which you looked at, or an SE ResNext. You'll see EfficientNet sometimes, DenseNet sometimes. So it's pretty much standard to use those, and the trick's always around how do you use the data, how do you set the problem up well, how do you do data augmentation so that you can get your model generalizing as well as possible, which is always the trick. All right. Well, if you have questions, shout them out. But I'll just get started. So this is kind of a fun lecture today. There's a lot in this. Hopefully, we'll get through it all. But we're going to cover a number of ways in which we can think about what convolutional networks have learned, and by various ways of visualizing them. There's a lot of cool, fun ideas. Some of our homework for the next time, for homework 3, will have you kind of work with some of these ideas. So you get to try them out for yourself, and they're pretty fun. So yeah, the question is, what's going on inside these convnets? Especially the deeper we go, what's happening at a particular layer? What's it contributing to the overall performance of the model? Or how would we even begin to ask that question? So one way to think about this is to think, well, okay, at every layer there's every convolutional layer there's a kind of spatially extended thing going on. So what is that spatially extended thing? So we've looked at this before. You can look at you can pretty easily visualize the first layer in your network, and in particular, you can look at you can visualize these in a pretty straightforward way, because in your first layer, this is to do the first transformation of your input, and so you only have 3 filters, right? You have 3 filters, 3 channels in this convolutional layer, and those should correspond to red, green, blue, because they're convolved with those particular channels in the input. And so you can just whichever architecture you have, there's going to be a certain number of those. You can take each one, and then you can just render it as a regular old 3-channel RGB image. And we looked at these before. We kind of dove in, thought about what each one what kinds of features it's activating for, right? So if you think about the patches of your input, doing a dot product with these, then if they're very aligned with the pattern, you're going to get a large large positive value there. If they're very anti-aligned with it, you're going to get a large negative value in it. And in many cases, you're just going to get roughly a 0 value, because it's orthogonal in some sense. It's has nothing to do with the filter. And the idea of training is that you're learning these things at this layer. So anyways, you can do this for all your networks, and almost always you get the same stuff for these kinds of data sets. So these are all trained on ImageNet. So for ImageNet, you almost always get the same kinds of filters, right? Look around, look at these. You see, you see your horizontal and vertical zebra patterns. You see kind of solid colors and variations on solid colors. You see, checkered patterns and things like that. You just go through each one of these. These are from different architectures. They're all pretty much the same. Remember, AlexNet has the first convolutional layer has an 11 by 11 filter, and in ResNets we have the initial layer is actually a 7 by 7 filter. So these are spatially smaller, but roughly you get the same kinds of things. So it's not all that interesting, to be honest. It's kind of cool to see that's what comes out, but it's not really all that interesting. It doesn't really tell you a whole lot about what's going on in the network. So the first thing you could think about doing is saying, well, I could just kind of go to any of the layers and sort of do the same thing, right? So if I go, if I take particular convolutional network, and I go and I look at the filters, there's going to be more than three. Typically there's going to be a lot more than 3 channels, so I can't just go and render these as a color image, but I can kind of just render each one on a grayscale and kind of get some idea of what's going on there, and I can do that at higher and higher layers. But again, there's not a whole lot there that's of interest. I mean, you can do this, but it's not going to tell you a whole lot. Mostly, it seems like kind of strange patterns. So there's got to be better ways to think about this. So today's lecture is all about all these different ways you can think about it, and there's many more than what we'll cover in this lecture. These are just a lot of the standard ideas, and then there's lots of variations on these ideas. People have improved on them or adapted them for certain situations or whatever. So here's one really interesting idea, and that is to think about what's actually in these final layers, these final fully connected layers before you transform into scores in preparation for applying your loss function. So for a lot of our networks, the AlexNets, like the BGGs and so forth, there were these large, in the case of those particular networks, 4,096 dimensional layers, right? And so if you now take an image and you forward it through the network, it's being transformed by each of these layers, and by the time it gets there, it's been turned into or compressed to a vector, in this case of size 4,096. So maybe we can start to learn something about what's going on in these networks by kind of thinking about those vectors. So one thing that's kind of cool to do is to represent all your data, all your images in this way, and then grab an image. So think about these images here as being your images of interest. Grab an image and transform it to its feature vector in that final layer, and then go look at all the other images with vectors, with feature vectors that are similar or in some sense close to the feature vector for that image. So if you do that and you look at this, what you see is a whole lot of similarity. So these are just some more or less random examples, although these are somewhat cherry picked, I'm sure. But you have this kind of purple flower, and if you now go look at in this, we sometimes call it an embedding space, the vector space for these feature vectors. We go into that vector space, we consider the vector that's the feature vector associated with that image, and then look at all the other images that have been embedded nearby it in that vector space, and we go back and look at their images. We can see there's a ton of similarity, right? So for the flowers, you see similarity in terms of the foreground color, the background color, the shape, the way that the flower is facing, and all kinds of similarities in that way. Similarly, if you look at each of the other images, you see other kinds of similarities. For the elephant, the ship, there's this jack-o'-lantern, dog, just particular species, and so forth. So, so that's kind of interesting, right? Is that by training these neural networks to classify the objects in these images, it's learned features that that have some kind of meaning to them, some kind of semantic meaning, like what is the actual content of this, and that meaning is preserved across similar images. So techniques like this power things like Google's ability to search by image, right? They don't take an image and then go look for all the nearest neighbors of that image. They do something like this where they embed it via some kind of trained neural network like this, and then they just look for nearest neighbors, some kind of however they measure similarity. That's very often to do with something like cosine distance. So just like vectors that make the smallest angles with that particular embedding vector. And then they say, okay, well, these are the nearest images, and you can go look, and sure, most of the time that makes a lot of sense, kind of semantically, why those were embedded similarly. Why does this happen? What's the reason why this happens? Yeah, that's right. And where is that? Like, where's that represented in your classifier network?
Here it would be like the vector that is at the closest point.
Yeah.
In this case, like the second vector of your 4096 by 10 dimensional final layer.
Mm-hmm.
Right?
Yeah. So, okay, yeah. So think about what's happening as you go from this final layer to the score layer. So like where you go from your choice of 4096 dimensions to 1,000 dimensions, which is is the number of classes you have. That's a matrix. The weights there, it's a matrix. That's 1,000 by 4096, and each row there. Remember this, going back to kind of like the first lectures we talked about linear classifiers. Each row there is like each row there corresponds to one of the classes, right? That's why there's 1,000 of them, and you're doing a dot product of the embedding at that layer of a particular image with the row in that matrix, which is sort of representing like the canonical or stereotypical representation of that class, right? And that's being learned because the whole task is to then take these scores, which are the dot products with these class vectors, and whichever one is largest ends up being the one that we being the class that we then assign to that to our test image, right? So the whole task is about for the correct class maximizing that dot product. And so how does that dot product get maximized? Well, you're changing those weights in that matrix 1,000 by 4096, and those rows are corresponding to something that matches up with it. So that's where that kind of like canonical, stereotypical, that like most representative vector is learned, or where it lives is it's in that matrix. So that's why this last layer is pretty interesting that way. Like it's literally it's literally like the layer that where we go from all these transformations to finally a number that gets evaluated for determining which class we are. So yeah. So anyways, that's where that comes from. So it's pretty cool. It's really useful actually. This notion of embedding, compressing or embedding your input into some smaller number of features. I mean, 4096 is huge in general. That's a huge vector space. We don't typically deal in those kinds of sizes, but it's much smaller than say the size of the image in terms of number of features. But you're compressing this down into features that sort of that have this kind of information for being able to do the classification problem. Now, if you change the task, that's gonna change. Like what gets embedded, by each other will change, right? If all of a sudden you change all the classes, or if you change the thing that you're trying to optimize, like if all of a sudden this went from a classification problem to say like like a segmentation problem, which we haven't talked about yet, but what information is being captured there is going to be different. But that's one of the very cool things about neural networks, is that you are learning features that are in some ways optimal for the task. And this is the innovation really of neural networks, is that up to neural networks have existed for a long time, but like other ways of doing machine learning that aren't like neural networks require you to somehow make some decisions about what features will go into the model. right? And here you're not doing that. Here you're just taking the data and allowing the architecture and the task to like figure out those features that are optimal for the task. Now, of course, it depends on the data set. And so if your data set is like really biased in one direction, like that's going to be sort of learned here. It's determined by the task and all these, all these things. But it is a way of being able to learn like task specific, data driven features. And so that's really, really important. Where I work full time, a pharmaceutical drug discovery company called Recursion, we transform images of cells into these vectors and do a lot of drug discovery via sort of the same kind of exploration of the resulting embedding space. And depending on how you set up your tasks and your data sets, you can get very, very informative compressions of your data to be able to do that kind of thing. It's very cool. Maybe somewhat subtle, but one of the most important reasons why we even use neural networks in the first place is this ability to do this. Okay, so enough time spent there. You can do, once you have a feature vector like this, you can do all kinds of stuff with it. One thing that's very often done, you can do this with really any layer, but it's to project these things into spaces in which you can visualize them. So you can think of doing things like PCA and keeping around 2 or 3 principal components and plotting your data points like in that 2 or 3 dimensional space. There are other algorithms like TSNE, UMAP, that will project your data down and get into low dimensions and give you some sense of like how that data is organized in the higher dimensional space. So this is like CFAR10 right here. If we had trained our model on CFAR10 and we take those high dimensional vectors, those embeddings, and then we project them down again to something like 2 dimensions using TSNE or something else, then oftentimes what we'll see is like a lot of structure preserved. So you see how, each sample is colored by the class that it's a part of. You can see how those are clustered together. So that clustering is happening here in the low dimensional space. We can assume it's happening in the high dimensional space as well, which makes sense again, right? Because what's happening is that something that's also really interesting to do is to also embed in this low dimensional visualization the class vectors from your last layer and see where they lie, and they're often kind of like the centroids of these clusters. So this can be a really interesting way of visualizing your data. It's fairly simple in this very simple kind of 10 class problem, but this can reveal a lot of information because somehow we're very visual. We understand visual information kind of very well, and we can understand it very quickly. And so if you can get it into that way, it can oftentimes give you a lot of sort of understanding of what your data set's like and what how the model sort of learned on that. And like other interesting things, here are classes that have an interface with each other, like which images are right there on the boundary. And a lot of times you'll see there's a lot of similarity there, right? They are from 2 different classes, but if you look at them, you can see that there's like some kind of, there's some reason to believe that maybe one could be interpreted, an image could be interpreted from the other class. This is very easy to see with like MNIST, like the 10 digits, 0 through 9. You'll see at these interfaces, zeros that look like 8s or 1s that look like 7s, and things like that.
So any one of these dots is one of the vectors of the weight matrix on the last layer?
No. These are all think of these as like the test samples. They've been embedded in the network, and then we've done one more dimension reduction to take them from, in this case, 4096 to 2 dimensions, and we're visualizing them here.
So any one of these
It's a sample from our test set. Yeah, exactly. What I was saying is, it's often, if you have a classifier, it's often a good idea to also embed in here the class vectors. In this case, like the 10 class vectors, because you'll often see them as being centroids within these clusters, because you know, how they, that's how they make a large dot product with the appropriate class vector, is that they're nearest to that. And if you've ever done, you know, dimension reduction, this, you know, that you kind of know what you're trying to do here, but this can actually be really, really powerful. Very often when you're exploring a data set, this is one of the best things you can do. Yeah, there's like fun, cool things that you can do with this. Okay, this is possibly one of the most interesting ways to think about what's going on in a neural network, but it's very kind of hard and expensive to do. And it's sort of fun, but like not super practical. But I'm going to share a video. This is a friend of mine, Jason Yazinski, who did a lot of this work a long time ago, actually, back in 2014, of just thinking about how do we understand, like how, you know, understand what networks are doing. He spent a lot of his career kind of doing that, exploring this, and we're going to watch the video for this. So we're going to learn about socks for a second. Underwear, sorry about that. All right.
Recent advances in neural networks have enabled computers to better see and understand the world. They can recognize school buses and zebras and can tell the difference between Maltese terriers and Yorkshire terriers. We now know what it takes to train these neural networks well, but we don't know so much about how they're actually computing their final answers. We developed this interactive deep visualization toolbox to shine light into these black boxes, showing what happens inside of neural nets. In the top left corner, we show the input to the network, which can be a still image or video from a webcam.
Are you trying to turn down the lights?
Sorry?
Are you trying to turn down the lights? Are you trying to turn down the lights?
No, I'm just trying to see
If the sound will go through? Oh, okay.
These black squares in the middle
How do you
show the
turn on these
activations
lights?
on a single layer of a network. In this case, the popular deep neural network called AlexNet running in Caffe. By interacting with the network, we can see what some of the neurons are doing. For example, on this first layer, the unit in the center responds strongly to light to dark edges. Its neighbor, one neuron over, responds to edges in the opposite direction.
Okay, sorry. So there's a little bit of confusion there, but do you kind of get what's going on here? Is what we're seeing here is we're not thinking about the filters anymore. What we're thinking about is that we're looking at the feature maps, the activations after particular layers, and we're seeing which of the neurons in those feature maps, you know, like so think of like the channels in the feature map, like the slices in the feature map. We're looking at each one of those slices here for a particular layer, and we're seeing that some of them become activated, you know, given certain stimuli. So it's a way of thinking about like what's been learned, you know, for this, like at this layer of the network. Does it make sense? Any questions on that? So yeah.
So each image in this square of images corresponds to a single filter.
Yes, but it's the whole. It's like the whole. So it's the output from that filter for the whole. For like, you know, if you're in your first convolutional layer, it's from the image. But if you're now like in a deeper, if you're in a higher layer, then it's from the feature map from before, the input from before, activating. But you know, it's running through, like this is the input, so it's running it through all the layers up to this point. But it's what we're looking at is, you know, if this is the image right now, we're looking, you know, this is convolutional layer 1. We're looking at we're looking at the total output, you know, from running one of the filters, you know, across the whole image. You know, each one of these squares corresponds to one of those filters, and so you're seeing all the filters simultaneously. And what you're seeing is that some of these filters, just on their own, you know, are capturing certain kinds of edges and things like that. But in particular, there are a few of these filters that are really capturing very strongly things like, you know, it's kind of like light to dark edges. And so I'm going to start this again and kind of go back.
Dark to light.
And so you can
Its
see
neighbor,
that.
one neuron over, responds to edges in the opposite. On this first layer, the unit in the center responds strongly to light to dark edges. Its neighbor, one neuron over,
see how many of those filters
responds to edges in the opposite
respond to
direction,
the
dark
text?
to light.
That's kind of cool too.
Using optimization, we can synthetically produce images that light up each neuron on this layer to see what each neuron is looking for.
Oops.
We can scroll through every layer in the network to see what it does, including convolution, pooling, and normalization layers. We can switch back and forth between showing the actual activations and showing images synthesized to produce high activation.
We'll talk about these in a sec.
By the time we get to the fifth convolutional layer, the features being computed represent abstract concepts. For example, this neuron seems to respond to faces. We can further investigate this neuron by showing a few different types of information.
Do you see how, so, you see how this is at a much lower resolution because we're deep in the network, right? So like we've been, there have been convolutional layers, but we've been doing like pooling and maybe we had like strides larger than one, and so we have a large, this is lower resolution, so this is like, that's why this is pixelated, but it's expanded to sort of cover or to match like the scale of the input image right here, right, which is a much higher resolution. So what he's saying is that in this higher layer, so this is like a COM5 layer, there are fewer pixels, but they seem to be working together to indicate that there is a face here. Look across the rest of these slices in the feature map from that from that conv layer. You don't see any other kind of activation like that. You can kind of look through these and wonder what they're doing. He'll kind of talk about some of the other ones, but this one is in particular, seems to be very strong for face, and he's going to kind of explore that now. Yeah.
First, we can artificially.
Yeah.
So in our homework, we're working with dropouts and things like that. So if this is like the face neuron, would they have not?
It's not the neuron. Remember, it's not the neuron,
Yeah.
right? Like, remember this is a whole. This is the output. So think about the transformations of convolutional layers, taking an image to like, to a feature map, which typically will have like 64 channels at that point.
Right.
And maybe this is growing to like 128.
Right.
Like I think we have like 128 here now, or something like that. I can't remember the numbers here. And we're looking at each slice in there. So it's not a single neuron. It's like all the neurons within that slice of the feature map.
Okay.
But they're all responding kind of jointly to the face here. Yeah. So like this layer or this slice, so like this filter in this layer is computing sort of face features. Yeah. Or really just an indicator of like, hey, face here,
Sorry, just to clarify, a neuron is just
Like one of the
number
units.
in
Yeah.
a weight matrix?
Yeah. Not in the weight matrix. This is a feature map. So this is the output. Yeah. Yeah.
Officially create optimized images using new regularization techniques that are described in our paper. These synthetic images show that this neuron fires in response to a face and shoulders. We can also plot the images from the training set that activate this neuron the most, as well as pixels from those images most responsible for the high activations, computed via the deconvolution technique. This feature responds to multiple faces at different locations, and by looking at the deconv, we can see that it would respond more strongly if we had even darker eyes and rosier lips. We can also confirm that it cares about the head and shoulders, but ignores the arms and torso. We can even see that it fires to some extent for cat faces. Using backprop or deconv, we can see that this unit depends most strongly on a couple of units in the previous layer conv4, and on about a dozen or so in conv3.
So this is something about how is the face channel in that output? How is that being built up out of previous outputs? And so it's kind of saying something about the filters associated with these slices in these earlier layers. Seem to be contributing to the ability to kind of put that all together as this high level abstract face output in the higher layer.
What does he mean by, I guess, 4.5 pictures? I don't know if I understand the math.
Yeah. So we're going to talk about some of these in this lecture, some of these techniques, but it's essentially a way of saying, a way of doing attribution, saying like, well, like my activations are this much right now in this COM5 feature map, like in this channel of the feature map. So it's saying, okay, well, how did they get to be that way? So it's basically a way of kind of getting the network to show you what contributed to those activations being high. So it's high activations in these other, these previous layers, the feature maps of these previous layers.
It's kind of like when we had like the one filter and you look at act over couples.
It's kind of like that.
So now we actually look at what specific ones.
Yeah. So it does depend on the receptive field. It does depend on that. But remember, what we have is these are the outputs. So like all of the neurons are there, and so yes, like each one of these is only going to depend on a certain subset of the certain subset of the output from the previous layer. But when you go across the whole of that slice in the feature map, eventually you've covered all of it, right? So again, each one of these little neurons in here is only responding to some small subset which is growing as you move backwards. But we're looking at the whole of it, so like it's in some sense considering the whole, like the whole of the previous input or the whole of the previous inputs from previous, even lower layers, even back to the input.
So is that gray image at the bottom? Is it showing the?
We'll talk about this one right here. This is a way of showing for this. Well, it was the layer that we're looking at. It's a way of being able to go back and look at the pixels and say, what would the pixels have to be like for that to be an even stronger response at that slice of the feature map.
So you're getting pretty much the partial derivative of the input with respect to that.
You're basically looking at each of those pixels, and there's a way of they use a particular technique for saying like something like what would the diff have to be with my image and like another image that would for that layer, for all those activations, for those to be even higher. So it's something like the idea is you're thinking about gradient ascent. So you're thinking about like how would I make those activations higher? You kind of back propagate now gradient ascent back all the way to the pixels, and then you have kind of like a regularized way of expressing that. So it's not just a mess of values. Typically, it's more like it's easier to interpret as like a visualization. It's pretty clever actually.
Is that gradient ascent type thing what you do like with a GAN?
No, it's not. But I think I know why you asked the question. We'll get the GANs. It's not the same. GAN's still using gradient descent to, well, let's just get there. It's a little bit too much to get into. GANs are still trying to minimize a loss. This is sort of like maximizing a like feature. So it's asking a slightly different question. Yeah.
Let's look at another neuron on this layer. So what's this unit doing? From the top 9 images, we might conclude that it fires for different types of clothing. But examining the synthetic images shows that it may be detecting not clothing per se, but wrinkles. In the live plot, we can see that it's activated by my shirt, and smoothing out half of my shirt causes that half of the activations to decrease. Finally, here's another interesting neuron. This one has learned to look for printed text in a variety of sizes, colors, and fonts. This is pretty cool, because we never asked the network to look for wrinkles or text or faces. The only labels we provided were at the very last layer, so the only reason the network learned features like text and faces in the middle was to support final decisions at that last layer. For example, the text detector may provide good evidence that a rectangle is in fact a book seen on edge, and detecting many books next to each other might be a good way of detecting a bookcase, which was one of the categories we trained the net to recognize. In this video, we've shown some of the features of the Deep Viz toolbox and a few of the things we've
Okay.
recommended.
Good enough. What's that?
Can you send up
The good news for you and everybody here is that this is linked already in the slides that are online. So yeah. And Jason's got all kinds of cool work on understanding what networks are doing, and he's a great like expositor of these ideas. All right, so the lights back on. Is it better if these lights are off? Probably is, huh? Okay, so that's pretty cool. That's like a whole bunch of different ideas all at once, but like just a kind of a nice video to see, just to get you thinking about like what exactly is happening in these kinds of networks, what they're learning. Okay, another way to think about this, like what's happening at certain layers, is to take certain activations. You can take one, you can take a small patch, and you can say, okay, which kinds of images are like maximally activating this neuron or this set of neurons. You know, it's kind of like it's like you're a neuroscientist, and you're like presenting your subject with stimuli, and you're measuring, you know, one or more neurons with like an electrode, and you're watching. You're like, you know, does certain stimuli elicit any response? And sometimes, you know, you will get a response, sometimes you won't. You're doing kind of the same thing here. You're being like an artificial neural network neuroscientist. And so if you do this, you can start to say, okay, well, for this neuron, this seems to be real, you know, this seems to be, so each of these rows is like the patches, or the patches of images that seem to maximally activate certain neurons. And we're just kind of picking some of these out of your network. And you can see that like the great variety of things that are responded to differentially, and you know, some of the similarities between them, right? So like if you take this row right here, there seems to be something about, you know, this kind of pattern of text, or at least like the colors in that like vertical orientation. There are other things that are also maximally activating it. So you can see that like these are very different from these, but there seems to be like a similarity in terms of how the image is divided up. Right? There's like a solid region that's narrower, fills the whole patch. And then there's a wider one. I don't know. Maybe it's lighter. I don't know. In contrast, who knows? Maybe it has text in it. Like this one kind of shows that would be different. Like the fact that this is just sort of divided up into this narrow and wide patch. So it's, I mean, you have to kind of reason about like what you're looking at, the cluster of images that you have that are maximally activating this. But it kind of can give you some interesting idea. You know, you see like people or like faces in like a certain orientation. Same thing with dogs. It's like these dark spots surrounded by light, coloring around them. I mean, these different patterns. I mean, you can just kind of play around with this kind of endlessly, and just sort of, like, if you think of it as sort of like classifying or like regrouping your images in a way that is determined by how much they activate certain neurons in your network. So it's kind of again, like another cool way to think about what's going on in networks. By the way, like what is this telling you about the network? Like if patches like this are like maximally activating certain neurons, you know, as you get higher and higher, deeper and deeper into the network, what is that sort of telling you? Yeah.
Like the whole feature map up to that neuron, through all the different layers, is kind of evolved to respond to that specific.
Yeah, and so what's that say about those kinds of, like these kinds of patterns here in particular?
That those are important for the neural networks and classification.
Yeah, exactly. Whatever the task is, being able to recognize patterns like this in the image is really important. It's exactly it. So, this, you can think about this as like being really interesting, right? Like this is kind of like something like an eye detector, that top row, right? It's like a lot of eyes look like this. Or maybe it's more abstract than that. Maybe it's like noses, like of animals, or I don't know, but this kind of configuration of pixels is really useful. Let's say you get a couple of those in a particular orientation on the, in your feature map, and you've likely narrowed down like the classes that this could possibly be by a lot, right? Because it's like maybe an animal of this certain size, or with eyes like this. I don't know. Same thing with the patterns. You can sort of reason through this and all this. Like look at this. This seems to be something like wheel-like. This would help you recognize cars and other vehicles. So this gives you kind of this feeling, or it's sort of building up evidence to this idea that networks are sort of building up hierarchical representations of what's in the image, hierarchical like spatially, right? Like different parts of the image, have these different kinds of things in it, and it's at these higher layers that you're sort of integrating that information together, which is cool. It's really, really cool. Okay, here's another way to think about like how to visualize these things or how to understand them. So the next set of techniques go under the type, like the topics or the theme of saliency and like occlusion. So what you're trying to do in these kinds of with these kinds of techniques is to think about the input and think about what parts of the input are really like important for the decisions that the network's making. So one way to do this is through what's called occlusion. So so let's say our network is trained really, really well, and imagine this image is filled in. This has actually been put over the top of this image, but just imagine it's filled in, and this image will be classified by this network with high confidence. It's going to have some very high probability or likelihood assigned to that particular class, right? So the score is much larger with the elephant class than any of the other classes. And that gets turned into a probability, and that's that probability. And so, maybe it's without that sort of gray square of pixels, maybe it's 0.99 or something like that, And then you throw in this gray square of basically like zeroed out the pixels in that region of the image. And now you just recompute the likelihood for that class being the likelihood of the correct class. And it's dropped a little bit. Let's say it was at 0.99, now it's at 0.95, but it's still really confident that that's an elephant. So what it means is that like those pixels don't really contribute a whole lot to understanding this as an elephant. But now if you zero out the pixels around like the head of the elephant, all of a sudden that likelihood drops a whole lot, down to something like 0.75. And so you can start to reason through this and say, oh, you know what? Those pixels are actually quite important for classifying this image correctly. Yeah.
Is there a reason they chose gray?
Well, it's just think of them as being zeroed out.
Wouldn't that be black?
Yeah, it's easier to see this. It's just think of it as being zeroed out. You really can kind of pick this to be anything you want, but like typically you just have a binary mask you put over the top of it, and if it's zero, everything gets zeroed out. Yeah.
If this were in like a training context, would this be similar to like drop block or like analogous to it?
There are data augmentation techniques that kind of look like this, that they do like cutout is what it's called, and cutout literally cuts out a piece of the image, and then you're asked to still classify it. So in this case, if this was cut out, we would still want this to learn that this was an elephant, and so it would do that by not relying on these pixels, but relying on all the rest of the pixels. So it's forcing it to say, well, maybe like in this case, like focusing on the tusks or something like that, right? So cutout is a pretty is a pretty standard data augmentation technique that one would use. There's other ones that do there's like mix up, where you do this kind of cutout, but then you replace it with the same region from a different image, and it could be from a totally different class. And now your label is not just, there's an elephant here, but there's like, remember that this is cross entropy, so you're actually giving it a vector of like the distribution of classes here. So like whatever like the fraction of the image that corresponds to the one class, like that becomes like in that vector over your classes, you put that fraction there, and then the rest of the weight would go to the other class, and you train with that. Actually, it's really powerful, called mix-up. There's all kinds of variations like that. I didn't mean to get into it here, but this is just simply, the idea of occlusion. And then what you can do is you can kind of run that patch over the whole image, and you can produce these heat maps to show you something like, where does think of the color that's here as like the center of the patch. And then, these are the corresponding probabilities. So as as these values go down, that indicates that those pixels were very important, or the pixels, that would have been cut out when you put that patch in the centered there. The pixels that are cut out are very important for making that prediction. And so you use this heat map, and you can look at this and you can say like, oh yeah, that makes a lot of sense, right? Like this seems to give you, like the shape of the boat down here. Like these are all really important pixels. Some of the sails are important. The elephant head is important. Go-karts, like the actual go-karts are, they have lower numbers as you cut them out. So it's a way to do this. It's actually very expensive to do this, unfortunately, but it can be done, and gives you these kind of neat heat maps. So that's occlusion. Saliency is basically is trying to get at the same idea. Saliency is trying to say which pixels were salient in the decision to in the case of classification, to choose the class that we did for this image. And so the idea is when we forward an image through our network, we get to the softmax, and those are all the likelihoods for this image being, having an object of that class there, right? And so, you'd want the dog class to have the largest probability there, or likelihood there, out of all the other classes, right? You want this to be 0.9 something, and the rest to be all really small. A good classifier, a very confident classifier would look like that. But now what you can do is you can do this kind of idea of backpropagating, backpropagating, but instead of backpropagating from the loss, you backpropagate from that score. And so what you're trying to do is you're trying to basically you're trying to change the pixels. So think about what backpropagation is doing. Backpropagation is saying, it's giving you, you're learning to compute, the partial derivative of your, whatever it is that you care about, in this case, like the score for the correct class of dog, with respect to in this case, we want to go back to each of the pixels individually. And what that will tell you is the direction that you ought to change. Once you computed those gradients, that'll tell you the direction in which you ought to change that pixel, each individual pixel, to increase that score, right? So like that's like the whole idea of like why we do backpropagation is we're computing these. We actually use the algorithm to compute the gradients of the loss with respect to the weights, and then we use that information to do gradient descent. But if we just use backpropagation itself without doing the weight step and go all the way back to the pixels from the score, what we're really getting is just the gradient for the score with respect to each of the pixels. So that says, should we increase or decrease, and to what extent, should we increase or decrease this particular pixel to increase the score for dog. And so if we sort of visualize those, the magnitudes of those gradients at each of the pixels, what we get is something kind of like what we just saw in the occlusion study, where pixels, in this case, the black background is going to be 0, and things that are lighter are going to be larger and larger gradients. this is going to show us which pixels seem, if we change these pixels, we would be increasing the score, the likelihood that this image would be classified as dog. And you can see how this has picked out all the pixels around the dog itself. It hasn't picked out anything in the background. So changing the background won't help at all. But changing, changing the intensity essentially of these pixels is, would increase that. So, something like here where it's quite strong is something about like that particular leg. If somehow we made that leg look maybe more dog-like by making it darker or something like that. I don't know. But the point is that if a technique like this tends to focus in on what semantically makes sense, like which pixels are maximally contributing to the score. Now it's kind of funny, right? Because we've already trained the network, so all the weights are set. We're just using the network to then back propagate. So the weights are all fixed. We're just back propagating the score through back to the pixels. So given the weights, given this data point, we're saying, how could I change this data point so that I get a higher score? And so, so this is a class. We're going to talk some more about this, but this is a class of algorithms that can be used. You can. It's fairly efficient because you're just using backpropagation, which we know is really efficient, on GPUs and things like that. And you can get this sort of array over the whole image, which is really pretty cool. Yeah, go ahead.
Is that picture telling us that we should make the pixels over there brighter? So our dog should be brighter and we'll get a maximum.
So brighter is kind of, not exactly. Because remember what we have is we have gradients over our 3 channels, and they could be positive or they could be negative. The point is that what we really do is we look at the absolute value of each of those over all the channels. Like in this particular one, we just look at the max over those 3 channels. So it's not that it would make it brighter. It's that if we make a large change, or if we make a change to this pixel, in the particular direction, although we're kind of, for the visualization, we kind of ignore the direction. We just seeing that this was large. If we make a change there, then we're going to see a large change in the score, or larger, at least relative to the rest of the pixels.
So it's not that we'll get a better score if we change those pixels, then we'll change.
Well, yes, we are going to get a better score if we change it in the right direction.
Yeah.
Like if we took a step. So if we do the back propagation and then we took a step where we use those gradients and adjusted all the pixels, these are the ones that would be adjusted. It's not necessarily that maybe they could change color, or maybe they could become brighter, or whatever else. But we're gonna if we make changes to these ones according to that, then we're gonna have a greater dog score. And the point is that it's focusing on the pixels that matter in this image, right? It's not perfect. This is very cloudy, and there's ways of making this much better in terms of visualization, but it does make a lot of sense, given where the dog is in the image. Is that making sense? So saliency is a very cool way to think about, to understand what it is, basically doing attribution. Which pixels in your image are contributing to the score that you're getting?
Are we taking derivative of the input with respect to the entire score vector, or is it
No, you're just of the correct class. And it's said the other way around. We're taking the derivative of the score with respect to the pixels. Yeah. And you can do these for all your images and all your classes. Right? So I don't know, steam rays, some kind of rays, tractor, some fruit, dog, sailboat. Sort of makes sense with what comes out of these. This has been completely improved on since this time, but what a lot of people noticed was that you could sort of use this as input to do segmentation of your images for just the object within that image. There are particular kinds of algorithms for that go under like the umbrella of max cut algorithms, and sort of you could start with this and thinking of this in a kind of like graphical way, and this would allow you to correctly cut out, or cut out most of the pixels that were associated with the object in the image. So that's kind of cool. This has been, there's lots and lots of ways that you can improve on this, but it's really quite cool. And the point about this segmentation without supervision is we didn't supervise it with like a segmentation mask. We simply supervised it with just like the fact that there was a class, just a straightforward classification problem. So that's kind of cool. All right, so how can you make that a bit better? So it turns out people kind of started looking into this, like how to make this better. One very simple way to make this better is to only backpropagate positive gradients. So if you look at each layer, you're gonna have positive gradients and negative gradients that as you do backpropagation at each layer, and multiplying that with the downstream gradient. So if you only backpropagate the positive gradients, you tend to get better results. And not only that, you can start to interpret these things as like you can color these things, because remember that these we're backpropagating all the way through to the images. So we have a gradient on each of the colors at each pixel, and so we can color these. So this is now what we were seeing before, but we're instead of taking so we have only positive values now. So instead of like taking the absolute value and then taking the max over the three color channels, we actually just have positive values, and we just plot those as if they were colors. Again, these are gradients, and this is what we were kind of seeing before when you saw those kind of funny pictures of Jason and Jeff Kloon, who was the other person, where it was showing like he said something like if we had rosier lips, these activations would be even more activated. So it's the same idea. So again, remember these images came from looking at particular neurons in a feature map. So if we focus on those, we could get that neuron to fire even more if we changed that image, in this color direction. Whatever kind of color that is, in that color direction, it would even be more, activated more that like nose-like pattern or the other patterns that are there. So that's kind of where that comes from. And you can see how this is focusing. This is really cool, right? Because we were asking this question, like, what is it that this is seeing here? In particular, this last row we were looking at it and saying, well, what is it about these images that is causing this neuron to be very activated? And you can look at these and you can see it really is this kind of dividing line between these two sides, and something about like there being a kind of a horizontal pattern on to the right of that dividing line. So it's starting to give you a lot of information. Now you should be asking yourself, well, what does it matter if I know this about one neuron? Like, this is a lot of work just to like think about one neuron, and it, it's kind of true, but it's if you apply this to your scores, it's often be very helpful. Now, the thing that you should be thinking about is, okay, well, if I can do this and I can like think about the like a particular image, and I can change the pixels such that I get like a higher score. What if I like is there like a maximal image? Is there like a whole image that maximally like that'll give me like the highest like score for that particular class? And so you can continue to like apply these ideas and actually do that. So what we want to do, we want to actually generate a synthetic image that maximally activates a neuron or maximizes the score associated with a particular class. And the way that you do that is you simply take whatever that is, like say this is the score for a particular class, and you just you know, you're going to run gradient ascent. You want to maximize. So this is an image. This eye is an image. So it's all the pixels. We want to pick the image that maximizes that score. And so how do we do that? Well, we start from some starting point, usually kind of randomized or like zero pixel values, and then we're going to do gradient ascent and do these steps to kind of build up this image. Oftentimes we put like a regularizer on this procedure as well, so that we don't get like super crazy. Like we want this to kind of look like an image, and so oftentimes these impose a kind of smoothness amongst the pixel values. So it's not just like this jarring, you know. When we look at natural scenes, like this has to do with the data set. So when we look at natural scenes, we don't typically see like pixels, you know, going from one pixel to another, everything changing very rapidly. We tend to see kind of smooth transitions, and so oftentimes this will be like something that will penalize an arrangement of pixels where you have very sharp transitions from pixel to pixel, and this will smooth it out. And if we do that, we do gradient ascent, start from, in this case, an example here is like a zero image, then we can start to really we can produce these images, and it's super cool. So what do you get? So we go back to our ImageNet, our network trained on ImageNet, and we pick one of the classes. So here's 6 classes from ImageNet. We have dumbbell cup, Dalmatian, bell pepper, lemon, husky. By the way, ImageNet has tons and tons of classes for different species of dogs for some reason. It's probably because there's a lot of dog pictures on the internet. That's really what it comes down to. But so this is what you get from starting from 0 and then running this, this gradient ascent on the pixels to maximize, in this case, the dumbbell class score, or the cup class score, the Dalmatian class score, and so forth. And so, tell me about what you're seeing here. Is this, when I was explaining what we were going to do, is this what you expected? Kind of? Okay, so like, no, yeah, kind of. Anybody just like, yes, this is what I totally expected. Yeah. No, it's not what you're expecting, because like, this doesn't look like like any natural image, but this is maximizing. So think about that for a second. It's maximizing the score. Like, why do you think it's maximizing the score? Just throw some ideas out there. Pick one of these. Let's pick, maybe this is easier to go with. Let's pick lemon here. Why would that in some sense be maximizing the score?
Probably like, we sort of like when we were doing our original the 10 images, right, the cars, horses, things like that. You can see the horse, and the horse had 2 heads to it, which isn't what you would actually expect to see with a horse, but from its perspective, like, if it were to see 2 horses, it would like extra matching or whatever. I guess from this perspective, just the different angles you can get from a lemon and everything all gets deposited in a single image, and it's us, but to it, it's like, yeah, it's everything.
Yeah, that's going the right direction for sure. It's like this is. So first of all, you can kind of see some lemons in here. I mean, sort of, right? Like this kind of looks like a lemon. This kind of looks like lemon. This kind of looks like there's a bit of a lemon shape. There's definitely a yellow color, but they're like kind of all over the place, and they're in different orientations. And what's weird is that they're not all like really yellow. Actually, I don't really have a good explanation for that, to be honest. They're not really all that yellow. But notice like how the textures change as you're like in a lemon and in between them, and then they're kind of all spread out, right? So like these all together sort of maximize that score. So like if an image came along like this would be like, man, that is a lemon. And again, the reason is sort of like there's like lemon-like things all over the image, and it's not just that there's like the object. It's like the kind of things that make for a lemon. So it's sort of unsatisfying in ways. In fact, we're about to talk about something about these networks that they're very brittle with respect to classification, and it has to do something with like the fact that these are what maximize the classes. And if you look now at all the rest of these, you can kind of see the same kinds of things. Like, look at these Dalmatians. There's like 3 different Dalmatians here, sort of. Like, kind of one. This is like the rear end and like the face, the head. There's one kind of like going this way. There's one, I think, walking that direction. It's kind of hard to tell. You can see the checker, or not the checker, but the spotted pattern is black and white. And again, it's kind of like you were saying. It's like the horse and two, like with two heads. It's like these dogs in these positions are sort of like the stereotypical ways in which these show up in the images. Same thing with for the lemons, and like kind of in these arrangements. And if I have a lot of these, all represented, I'm going to get like, this is absolutely Dalmatian and so forth. Dumbbell, you can kind of see that. I mean, like dumbbell is super weird, but a lot of like cylinders with like, wide short cylinders on long narrow cylinders. Anyways, super interesting. I think this starts to just be fascinating when you start to think about like what's really going on here, what these things are really learning. Yeah.
Do you think you could use this to detect like biases in the data?
I mean, not really detect biases, but like I think it can give you intuitions for maybe like that it has certain biases. Like have it generate a woman, for instance. Like what does it think a woman is, or a man, or I don't know, like some. I mean, I don't think man and women are actually ImageNet classes, but if you had that in your data set, you could do that, right? And like that would give you some, like the stereotypical, like what it thinks a man or a woman is, or maybe pick a certain race or something like that. And so these were the biases. It would kind of demonstrate the biases. Although these are really hard to kind of reason about, right? Like they're very. So there's like ways of improving these that maybe are better. You can keep going. Yeah, there's like ways to make this better. So I won't get into the details of that. We're starting to run out of time. But you can, there's ways of kind of regularizing what you do, and it's sort of a little more satisfying what you see. Like this really looks a lot more like a couple of pelicans, By the way, this is from different random starts. This, cobras, beetles, it's a little more satisfying what you see there, and maybe it makes a little more sense. Yeah, keep going. You can do this for all your layers, right? So we were talking about we were talking about the scores, but we can think about intermediate features for all of these, and get some understanding of like what that layer of representation is, most important, say, for particular classes. Let's see. I'm going to try to catch up a little bit because we're a little bit behind. You can even make this better. Whoops. You can make this even better by doing this multifaceted approach where you have sort of a number of different bits of evidence that you're bringing together for maximizing, a particular class, like in this case, the grocery store, and you can see what you get out of this, right? So like now it starts to look a lot more like maybe what you were expecting at the beginning of this. Like jack-o'-lantern, that's pretty spooky. But like that's a pretty standard, jack-o'-lantern. Hourglass, grand piano, gown, keep going, This might be the kind of thing you want to look at to think about bias. But basically what this is doing now is, this is using multiple ways, multiple different bits of evidence for like what it means to maximize for this class, bring them together and regularizing that so that you get sort of color profiles, shape profiles, and you can bring this all together in a way that really looks a lot more interpretable, a lot more believable, a lot more like a natural scene. I mean, obviously, none of these are natural scenes. They all look like paintings, right? They all look like sort of dreamlike. They have a kind of that kind of cloudy, aspect to them. But yeah, but pretty cool that you can go from this idea of like saliency all the way to something like this, where you can generate these synthetic images that are sort of stereotypical, prototypical for your classes. Here's some more examples. That was from a different layer, by the way. Okay, this is what I want to make sure to cover. This is quite interesting. Okay, so fooling our classifier. So like to this point, we took a training classifier, something that was really good at classifying the ImageNet, and we used it to like have it tell us where the pixels are that are sort of most important for determining a class. We used it to generate synthetic images for particular classes and related ideas. But now we can use those very networks to fool the network. And here's how that works. So you start with, it says arbitrary image. Let's just start with any image, and then just pick another class. Okay. Now your job, you're an adversary. So the network right now is really good at classifying that image as whatever class, whatever objects in that image. But you want it to classify. You want to make it so that it classifies. You want to change some pixels so that it classifies that image incorrectly. So you pick another class, just any other class, and then what do? Well, you use the techniques that we just talked about, and you backpropagate you do backpropagation from the score of the incorrect class to the pixels on the image of the other class, and then you change those pixels, and you change them in the direction that's going to maximize that score. So we're pushing towards the network, thinking more and more that the other image is in there. So the question to you all is, how much is this going to change the image? Let's say we're looking at take bell pepper and Dalmatian. If I start with the bell pepper image and I want to make the network classify it as a Dalmatian, so I start to adjust the pixels via backpropagation to increase the score on Dalmatian. What do you think that image is going to look like?
Might not even notice.
Might not even notice. Okay, that's an option. Yeah.
Well, it depends on your learning rate, right? How far you step away.
Yeah, right. Let's say we just use we're taking small steps so that we have all the time in the world. We take small steps so that we're we're making it's a greedy algorithm. We're making the best kind of local decisions that we can.
And
We're not just stepping over it.
Like a local minima, and so it's not going to go very far from your original minima.
Okay, well, but it's going to go, if it has gradient to go up, it'll just go up. It might just take a long time. Yeah. But we're not going to do anything crazy like we're going to step over big, maxima or something like that, or new minima. So what's the image going to look like? Is it going to be some blend between bell peppers and Dalmatians? So it turns out that you don't have to change it very much to have this classified as a totally different image or totally different object. You have to have a totally different object. So here's an example. Here's that same African elephant image. We do this procedure a couple of times, a couple of iterations. Here is the difference between these two images. This is a visualization of the difference. So this is basically no difference. Here's 10x that. So you can see there is some structure to this. Well, there is a chain, but this is at 10 times what this is. So this is the actual change. This is 10 times, so you can kind of visualize it. So some very, very, to us, imperceptible changes. If I were to ask you, is there any difference between these two images, you would likely have said no. But the network no longer thinks the same thing as you do. It now thinks this is a koala. Yeah.
So if you could take a neural network you've trained on a training set and create an adversarial version of all of the images in the training set, would it be valuable to feed those images and continue training the net that you already have on?
Yeah. So people have kind of pitched that as a way to make these more robust. And the way that this has a name, it's epsilon tubes. So the idea is that you're there's a manifold. So if you think about how we project all that data into 2 dimensions, there's these data manifolds. So in some abstract space, our classes kind of live in this space, and what you're doing is it's a kind of regularization that's saying around that manifold I'm making these kind of small imperceptible changes, and so that if I kind of fatten up that manifold to be to have these kinds of directions, so I'm sort of it's hard to imagine this unless you spend all your graduate school doing math, and then you're oh, that was easy. But it's also kind of a weird waste of time. But anyways, so you have this data manifold in a high dimensional space, and now you're just kind of fattening it up so that everything nearby it also gets classified as you know, as the same class like as you're near it, right? That's kind of what that would be doing. People do that, but it's like super wasteful. It's really hard to do. And it's really like incomplete in the sense that you could do that as much as you want. You could still, and then like the next time you can just still make another one of these. So it's super weird. Like it's like the important thing to get from this is like probably how you were thinking about how these things work is not how they work, because just this very small change in this arrangement of pixels made a koala. So what is it about this? Well, it's some sort of like statistical, you know, there's some kind of relationship amongst all these pixels that makes it more koala-like. I mean, I kind of like that. Maybe I can kind of fake myself into thinking like, oh yeah, maybe it's got kind of like a koala-like thing there, you know? I don't know, but not really. I don't know. Like, you know, humans are awesome at like being able to like look at a thing that's happened and give an explanation for it, even if it's totally wrong. We're like super good at that, and it's a particularly poor part of our rational lives. But yeah, I don't know. Like this is really a problem, and no one's really come up with in the decade or so. Well, it's a little less than a decade that people have known this existed and been working on it. No one's really given like a satisfactory this is how you deal with this.
So in other words, like regardless of what network you have or if you train on adversarial examples or whatever you do, always have more.
I mean, there are like limited ways like in which you interpret like the universe, like your input data set, like that universe of data that where I think you can get guarantees of like being robust I think in the sense of like epsilon fattening of the your manifold, but like I don't know this area super well, but I don't think there's anything there that like the networks that you and I and everybody else is going to be training would make them not susceptible to this issue. It's essentially saying something deep about how neural networks work and how they are possibly like all like irreversibly or irreversibly not irreversibly, what's the right word? They are we are unable to kind of correct this about them.
Inevitably.
Yeah, maybe that's inevitably. It's not really that either. It's sort of like I'll go. Inevitably is a good one. We'll go with that. Thank you for the suggestion. They're inevitably going to have this issue. We're not going to get into that today because we only have a few minutes. I'm not going to get through everything today. There's a link here to a great lecture on this. I'll finish up with this. There's a few more things on here, but we're just going to do it next time and then go on to the next part of the lectures. So this is pretty cool. So this is very much like what we were just looking at. But what you do is you do back propagation, but when you calculate the gradients, you don't actually calculate the gradients. You actually just use the activations as the gradients. So this is called Deep Dream. When this came out, like the whole world, like the whole AI world was like, whoa, dreaming. They're like imagining things. I don't know. We seem to like anthropomorphize these things like as fast as we can, but the idea is that we're gonna adjust an image. We're gonna start with an image and we're gonna adjust it. And the way that we're gonna adjust it is when we do back propagation, we're actually just gonna use the activation. So think about what that means. That means that if a pixel or a neuron in a feature map is highly activated, then the gradient there is going to be very large in that same direction. And so that's gonna have the effect of sort of amplifying activations all over the network. So what happens? So if you use this signal to adjust your pixels, what do you get? So here's the original image, and by the way, we're using this blue sky with clouds because we're daydreaming, we're dreaming. So what happens? Well, you get this like psychedelic sort of trippy. I mean, if anybody wants to tell us about what an acid trip's like, I don't know. but I'm imagining it's kind of got stuff like this in it. It's wild, right? Like, just kind of look at this for a little while. And then I'm going to show you something about this. Look, there are like coherent shapes in here. There's like, I don't know, this is kind of like a bird on like a bird body, but that body is wrong. It's got some legs, but it's just sort of wrong. You know, it's kind of like, there's like a hedgehog thing down here. There's like this snail, but I don't know, like some mammal coming out of it. Like, what is going on here? There's like these cathedral church-like things. There's like a space needle over there. What is going on? You know, people started to like look into these and give these names. You have the admiral dog, the pig snail, the camel bird. So what is going on here? People started to colorize these things and sell them as art. What's going on here?
So hold on. This is maximizing. Like, you take an image and then you maximize for the class that it classified it as, or you're maximizing for.
What you're doing is you're taking an image and you're forwarding it through the network to some point, and then you're going to do backpropagation. Like there's nothing you're going to you're going to do backpropagation. There's like nothing downstream that you're actually like optimizing. You're just going to kind of like start at some point in the network, and you're just going to say, okay, the gradients that I'm going to use here are the actual activations from the forward pass. And so it's a way of like bootstrapping the activations to be greater and greater. So like whatever that image was like activating, that gradient step's going to activate it even more, right? Because it's like, if the activation was high, then the gradient's high, and then that is going to have the effect of making that activation even higher. It's going to do it all throughout the network. Do you have a question?
But that's not really backpropagation.
Yeah, backpropagation is just a way of like computing gradients, right? From any place, but we're going to pretend like there was something downstream and start with just like those gradients at all the neurons, all the activations in that feature map, and then pass that back all the way to the pixels, and then update the pixels, and we're going to keep doing that. So it's like this sort of like self-reinforcing signal, and this is like what comes out of it. So like, what is coming out of it? And these things just get wild, you know? So like, what is going on here? What are we seeing? We got to end here. So what are we seeing? What does this tell us about the network? Remember, this is all about like understanding what's going on with convolutional networks.
Would this just be all of the different features it can recognize?
Okay, like possibly, yeah. Something like that. Keep building on that. Some thoughts. What's going on here?
Well, I guess like the fact that you might pull these out of a blank sky and shows it like anything, like any image is pretty close to any of the other like features, like it's close to activating.
Yeah. So look at this and look at this. So back, forth. So like maybe, what was this called? Admiral dog or something like that? Whatever. Like, look at this thing right here for a second. If I go back and forth, there's kind of reason why it is where it is, right? Just given like what the original input image is there. So when you do this thing, you're basically getting it to like, you're getting it to sort of you're like expanding on what it's tuned to see. Remember, these networks have been trained on like 1,000 objects in these images, right? So like it wants to see objects. You know, it wants to see them everywhere, right? And it wants to see the things that are objects. So when it sees this, it's like this is an object. This, like, what is this? This isn't anything. Like, what do I think is there? Like it has all these activations, and then it says, okay, well, I'm going to start to reinforce those, and I'm going to keep reinforcing those. And then to eventually what I've got is like these crazy, you know, like aggregations of like different things that are kind of like in the data set that it's learned to classify. And so what you're seeing is, you know, think about it this way. These networks have learned to encode these kinds of objects. When you run this algorithm, you're forcing it to sort of like show you the things it thinks are there in the image. Obviously they're not there, but it's like, you know, it's like a self-reinforcing thing. So as soon as like a little bit of structure pops up, then a lot more pops up, and you get this kind of craziness. So it's like, it's another way of kind of thinking about how the network is sort of composing all the things it's learned about, you know, into like coherent objects.
So you could kind of look at these as like false leads. Like the network has recognized there might be a pigeon head here, but then that kind of got filtered out.
Yeah, right.
Down, so it didn't classify.
Yeah, exactly. Exactly. But it's not really. It doesn't really care that there's a pigeon head there. It just knows that, like, man, if there was stuff like this here, I would totally classify that. You know. So it's kind of doing that. It's like, oh man, I think there's a thing there. I'm just gonna make it be there. And it's just doing this all over, and you know, you get this kind of wild stuff. So again, like, I wouldn't call this as very useful for understanding what your networks, you know, has learned, but it's sort of another view into what has been learned, and it's very, very dependent, obviously, on your data set. If we took another classifier, just another trained network for a totally different data set, and ran it on this, we would get something very similar in terms of like structure coming out of it, but it would be structure that would be relevant to that particular data set. So like, we were taking like the data we produce at our company and ran this, we'd see a lot of like cell-like things, you know. So something along those lines. Anyways, I kept you a long time. I'm sorry about that, but I appreciate you staying. And there's a few more ideas here that are particularly important for homework 3. We'll talk about them next time and do the next lecture.
Quick question. You never got to decorrelated batch norm in your last lecture. When should one use like decorrelated batch norm versus normal batch norm?
Never.
Okay.